Now let's finally go ahead and carry out the construction of some simple models. Let's call them basic. Actually, we have already discussed the issues that are involved in the construction. So I'm just going to introduce two models that are going to serve two purposes. One, you see some examples, and two, you see these examples in contexts that are important in application. Nevertheless, the way I am going to introduce them is primarily to acquaint you with the intricacies of nonlinear elasticity. And really, I'm not trying to be perfect with respect to the, let me say, realities. In other words, for instance, I will call these functions the Fung model. And a model that is, let's say, neo-Hookean, so it's the new version of the Hooke model, neo-Hooke model, that these are the way I'm going to call them. But really, if you eventually in the future look at the neo-Hooke model, you see that the function I'm about to write plays a role certainly in the neo-Hooke model, but there are other factors that are dominant in that model. Similarly, modern biomechanical models for soft tissue certainly employ many different types of strain energy functions. The one I'm writing here is one that sort of has classically appeared in one point, certainly enough for us at this point to, again, acquaint ourselves with the intricacies of nonlinear elasticity. Now, the first model that I'm writing here, the Fung model, is primarily for tissue, soft tissue, whereas the other one is primarily for soft polymers. Let's say, as a very good example of technological interest, rubber. Okay, and so let's divide our discussion into these two basic formulations. Okay, now primarily these are going to also help me demonstrate two general aspects of the stress versus stretch curve. Namely that stress stretch curve could be either one that is sort of ever increasing but with a changing slope that is either continuously increasing or continuously decreasing. So here we have increasing slope, here we have decreasing slope. And remember that the guiding aspect is that the stress is going to be a function of the stretch, and in all cases the stress has to be associated with the strain energy per unit volume in the material, and that is what we called the strain energy function C. So this is the central aspect that we're trying to input, and so we go ahead and propose a form for C, the strain energy function. So in the Fung model, we've already sort of indicatively worked on that when we were trying to think about the aspects that govern the form of the strain energy function. So I'm just going to write down a form Now, that's the form of the strain energy function, which I'm going to call the Fung model. Notice that if you plug in lambda equals 1, this is 1, that's also 1. So unless alpha is equal to 1, this thing is not equal to 0. So I get some amount of energy, although it is, although the material is not deforming. To reset that to a value of 0, here I really need to have a constant. But notice that eventually when I calculate the stress, I'm just going to take the derivative of this, and that constant is not going to play a role. That's why I said earlier that adjusting this so that we get 0 energy at no deformation, it is nice, but not a great requirement. On the other hand, for stress, we certainly should have zero stress at no deformation. So that is how we calculate it. And so if you just go ahead and take the derivative, you're just going to find this relation between stress and deformation. Now you can go ahead and look at the slope as well. The slope is going to be equal to del sigma over del lambda, which is E, the Young's modulus alpha to the power lambda minus 1. Okay, and you see that it is ever increasing. Now, in the case of the neo-Hooke model, it's a different function that we're going to write. In this case, we had some linear contribution, certainly, that serves the purpose of setting the stress to a value of 0 when lambda is equal to 1. The dominating term, therefore, is really this part over here, which is exponential. It's much more than a quadratic. So here, we will also have much more than a quadratic. We do start off with a quadratic term. We know that alone is not going to be sufficient for sure, but then we throw in some natural logarithm of lambda minus 1. So once we do that, when we calculate the stress as the derivative of the strain energy function, we will get E over 2 lambda 1 minus lambda, which is now a nonlinear relation. In particular, if we calculate the slope, then the slope is going to be del sigma over del lambda. You can go ahead and plot these for representative values of the Young's modulus, for instance, and in this case of alpha as well, and see that they indeed look in the way I have depicted them. This is the way the slope looks. Okay. And if this slope, if the value of lambda keeps increasing with respect to 1, then you see that the slope is going to decrease and decrease further towards E over 2, a constant value, whereas at lambda equals 1, that value is E simply. Okay, so now when we look at these these two expressions, they have two qualitative, major qualitative features that I depicted here, but also there are some just quick advantages and disadvantages that I can immediately write down here. So first of all, notice that an advantage that this one has is the following. Actually, maybe it's better to start with the corresponding shortcoming of this one. Notice eventually that my form of the stress versus stretch curve should be such that I should be able to fit the data that I get from experiments. So to fit the data, I should have some free parameters. But here, I only have the Young's modulus, which is not a parameter that pertains to large deformations. I can already do a small deformation experiment and determine what the Young's modulus is. But in this case, we are looking at large deformations. I need to be able to fit this nonlinear curve beyond the region of small deformations, which is in the vicinity of lambda equals 1. So the shortcoming of this is that there are no such free parameters here. It's just the Young's modulus. So no free parameter except E, let's say. Certainly E is there, but really it's for small deformations already. So the advantage of this one is I have one such parameter, alpha. So there is a free parameter alpha to fit data better. Okay, now on the other hand, let us look at the shortcoming of this one. Now I told you that there are a certain number of expectations we have. Some of them are stronger than others, and ultimately what governs whether the model is good or not is how it works, how well it works under expected application scenarios. So now tissue, I just gave you an example that it's really often soft tissue is not expected to carry compressive loads. So not always, but often not expected to carry compressive loads. Now, therefore, so I can go here and plug in lambda equals 0. Remember, it means extremely compressive deformations. Epsilon is -1, right? So you're compressing the whole volume to 0. And we expect extremely large compressive stresses and extremely large, infinitely large strain energy values. But when I plug in lambda equals 0, what you get out of this is just a finite value of deformation. Go ahead and do that. Lambda equals 0. Everything will be a certain constant. Here as well, it will be a constant. So sigma 0 and c equals 0 at lambda equals 0 are finite. That is weird, but that is indeed because we don't expect tissue to carry really compressive loads. So really you should be using these things when lambda is actually larger than 1 in the tensile range. Okay, so otherwise you would be using it beyond its preferred level of or region of application, intended domain of application. Now on the other hand, when we look onto the other model, an advantage appears when we see that when you let lambda go to 0, the slope is blowing up, and that's because sigma goes to minus infinity, extremely large compressive stresses, infinitely large negative range as we expect, and also this term will blow up. And therefore, what we expect is that, what we see is that this neo-hook model works under both tension and compression. Okay. And so you might think, therefore, that, well, perhaps I have one model that does something well, another one that does another thing well. Well, why not take combinations of those? Because indeed, in the example that I gave you in the previous slide, I have indicated that sometimes you can have a data with decreasing slope and then an increasing slope, right? So perhaps I can combine these such that the stress versus stretch initially displays some decreasing slope and then switches to this one, say under tension, right? So these are motivating models that ultimately and subsequently you can take combinations of. And eventually the important thing is it doesn't matter what these were initially meant for. What matters ultimately is that you have some material which is very, let's say, soft, so that it can deform significantly under even small loads. That's what soft means in modern or practical terms. And I just want to fit the data as well as possible. So I can take combinations of suitable functions within their domains of application, and I can try to fit that data, and that's all a fair game, which is what we're going to comment on shortly next.